Hey guys, from today we will learn about new chapter. I will start from transformer, and yeah, today we will learn about first the principle of transformers, chapter one, and when it is no load operation, status. Let's see. So first of all, as you guys may know or didn't know, it doesn't matter. We will learn it together. Okay, don't worry. So why we need it? First of all, yeah, transformers looks like this. You know what I mean? But what I mean is why we first needed transformer first. Let's think first. In the past, this is a generator, and then this is a load, like our house, for example, like you know what I mean. So it's a load, and the generator is, close to the at the time, at first, time. But time goes by, the load is increased and generator is increased. That's why generator, to make electricity, it needed lots of, uh, the waters, you know what I mean, to cooling the generator. You know what I mean? We will learn it about the later generator. Just, yeah, you don't need to deeply learn it right now. Just because of we need it cooling the system. That's why generator go to near the river or sea. You know what I mean? Yeah, but so what I mean is that the problem is that look at that. So now generator is here, and then load is here. Load. It gotta be 1,000 kilometers or something more. You know what I mean? So the problem is here. Here's R and X. Oh, sorry. R and JX. You know what I mean? R plus JX. Yeah, problems. So if the current is going high, so the line, you know what I mean? Loss is line loss, LOSS. Sorry. Line loss is really big. You know what I mean? So line loss, P loss, is 1 over V22. That's why we increase the voltages. You know what I mean? So we generally step up from here, and then we step down near here. You know what I mean? So for example, uh, it generated 22K or 1AK. It increased 134K, or you know what I mean, more. There's a 765K, like more specific numbers. You know what I mean? We will do learning more about it, so don't worry. So the thing is, because of too much line loss, you know what I mean? That's why we have to increase the voltages, because V22 yeah, over 1 over V22. Got it? So what I mean is, yeah, that's why we made it like transformers. So first of all, transformer is looks like this. This is what is it? This is primary, and this is secondary. So primary, we need to think because we generally cannot see the generator, right? So we think just the primary part is as a generator. Think, and secondary is our load, as he mentioned. We just think like that. It's fine, right? And then this is steel, right? And as you guys can see here, laminate iron core. I guess I may mention about this because of the reduced eddy current. We laminate. Laminate means like a split, right? And then put together to reduce the eddy current. And this iron core is made in the silicon plate, right? Yeah, that's what we learned. Yeah, previous lecture. And then, yeah, here, look at that. And so we actually, we are kind of confused. Primary part and the secondary part is kind of, it looks like the diagram. The picture shows like it's kind of far away, right? But actually, it's in the same, you know, uh, plate. You know what I mean? So inside, you look at it here. Primary winding is here inside, right? There's winding. And then we're using the here insulator paper here, this part. And then we also cover the secondary winding. So generally we do is a prime winding is a low voltage side, and the insulating paper, and then high voltage like that. We generally, yeah, like a winding like this when you make a transformer. So here, look at that. So today we will about when it is no yeah, I will explain more about this. So this is transformers insulating paper. Here you can see, guys. So today we will first learn about the no load situation. No load, no load. That's the secondary part. Is it gotta be load here, right? Load. So first of all, as you guys know, this steel iron core, it has a saturation part. Yeah. If you guys don't know saturation meaning, go back to the lecture, and I mentioned about the hysteresis and the saturation part. You know what I mean? Have to learn it. So here is a I pi. I will make I pi a curve. So yeah, this is the saturation part, for example. So what I mean is I pi is actually at this, is L. It's indicated. So I wanna say is since look at that, it's open. So secondary part is doesn't work. You know what I mean? This is primary, right? So look at that. So we think Ohm's law. So here's I. We say this is uh, this current IO is exciting current. We say so IO equal. So here's X, right? The course, reactance is X, and then yeah, and then here's V, right? So we say this is for example, it's 134K, and X is it's 1,000 or more, and really big of ohms, like for example 3,000 ohm, and then 134K. You know what I mean? Like so what I mean is the IO exciting current is only the magnitude is we calculated the ohms law. You know what I mean? So yeah, this is really small. So there's a rated current, right? So it's gonna be 3 to 5% of magnitude of the rated current. You know what I mean? State current. You know what I mean? Yeah. Oh, and then yeah, I did explain about this. Here, look at that. And here E1 and E2. So look at that. Here, IOs coming, right? So look at that. This is X, right? X means now coil, right? So the current gonna be lagging. I will say just 90 degrees, right? So standard is V1 is 0 here, right? So IO, exciting current is here. But as I mentioned here, pi is I is like the same. I said different dimension, but same. It happened in the same pace. Like for example, me is I, and in front of a meter, there's in the mirror, I could see it me, right? So which means this in the mirror's me is pi, you know what I mean? So it happened the same time, but different dimension. So in page this. And pi, it's make it induced voltages, induced voltage E1 and E2. E1 and E2 is the same, you know, the in page, you know what I mean? The standard is. So as we learn the Faraday's law, induced voltage is no, this is let's just dt and d pi, right? The time goes by, the pi, if the pi is changing, the E is induced. That's why, you know what I mean? So this is a general situation of the at the no load situation, you know what I mean? The transformers, pager, you know, yeah, current and induced voltage, and how it, you know, works. And then yeah, only E1 and E2's, you know, it's in the same page, right? We now page. We wanna know the magnitude, right? Because we wanna know like this, right? We now know this is the same page, right? We now know this magnitude. It depending on the tons of winding n. So which means E1 equal to N1 dt and d pi. And 2 equal to N2 dt d pi. Because pi is the same, right? So it depending on the, you know, the tons. Yeah, how many wiring we did. Yeah. Yeah, that's it. And then yeah, look at that. I'll give you one question. This is now secondary part is open circuit, right? But E2 is induced or not? It's open circuit. Yeah. As you guys may think like no, you know, E2 is not induced, but actually it induced. Just that the current is not, you know, flowing, but E2 is induced here. The potential energy is here because of the law, Lenz's law. You know what I mean? Yeah, that's kind of amazing. And then here's a subtractive polarity and the additive polarity. What's the differences is here? You can see here dot 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 dot. So what I mean is the wiring is like look at that, like this, and then oh sorry, and then here also same. You know what I mean? Same direction like this. But for example, here additive is here. One part and the other part is you know what I mean? So different way. If it's going like this, and the second part also same way. But if it's going to from, you know, like this way, clockwise, but second part is, you know, counterclockwise. So the differences is we say subtractive polarity and the additive polarity, you know. So for example, incompatible hazards happened, like, you know, for example, like this circuits because of the insulation, you know, damages, it's you know, get together, closed, you know what I mean? Get together. So like this situation happened. Why we say subtractive? And subtractive polarity is a standard. As you guys can see here, uh, primary and secondary page is in phase, you know what I mean? But primary is, and then secondary is out of phase in the additive. Why? Look at that. For example, here, 1000 ohm and no 1000 ohm and 500 ohm. So current is gonna, I will change color. So the plus band. So current is gonna be, voltage is gonna be from here, and also this is from, so look at that, from here to here. It's reduced, so which means 500 volt left. But what about here? 1500, the 1500, more hazard, if the incompatible hazards happened, like, get together the lines, secondary and the primary windings, get together. Yeah, that is a difference. Oh, and yeah, I said I forget one thing here. Yeah, get that. So I said here is exciting current, right? Exciting current here. So as I said here, I pi, the curve is here. Here we say IO, right? So here is the saturation point, right? But IO is, depending on the Ohm's law, right? X is IO, right? IO. So we don't want a saturation, you know what I mean? If a saturation happens, the current is, it's really surgy, sudden increase, you know what I mean? I will explain. I already explained, but later we will, learning more about it. Don't worry. So we generally almost, using like this around because we wanna make more efficient, you know what I mean? Yeah. So by the way, we don't wanna get the ion cores getting the saturation, you know what I mean? But because of the money problem and the yeah, the efficiency, we also consider this, you know what I mean? Situation, consider the IO. IO is the exciting current is, only depending on the, Ohm's law. Yeah, today's lecture is done.